porque tiene ellos el modo.
No, pero je regarde la liste de modular déjà para que pugui sortir
students in their second half of the PhD to make an IT seminar presenting their work and their results. Our speaker today is Miguel Sierra, who has volunteered to tell us about his volunteer. He has kindly volunteered and we really appreciate it.
Highly recommended. Well, welcome everyone. Today I'm supposed to talk about my last project, which is about two-impurity systems, two-impurity magnetic systems, which was a collaboration with Rosa Lopez and Jocelyn. Although I'm going to explain this work, the actual goal of this seminar is more to make you understand what Kondo effect is than what I have done, because I think that it will be more useful for everybody to understand what is this effect. So also I encourage all of you, if you want to ask in the middle of the seminar, you are totally welcome to do it. Okay, and of course, this is the outline of the talk. I don't want to scare you. It's just to show you that I have put some effort to make you to understand what the Kondo effect is. Okay, let's start. So first, we are going to talk about metals. Let's consider a metal. What we can do with a metal. We can measure things, and what can we measure? We can measure currents or the resistance, and one thing that we can measure is the resistance due to temperature. So with this in mind, we go to our books, statistical physics books and solid state books, and we can do some find an expression for the resistance as a function of the temperature. We find here three contributions. One is the a constant, which is due to the defects of the metal. A second one is due to the electron interactions inside the metal. And the third one is the phonon contribution, is the vibrations of the lattice. So these three are combined. What it makes is that the resistivity of the resistance as a function of the temperature, it will increase as the temperature increases. But right now, let's go back almost a century ago. Let's go to 1934. And I'm going to show you one of the works made of these guys. And I'm going to focus on gold. And they show a graph of the resistance as a function of temperature. And they show you this. As you can see, as we lower the temperature, of course, it gets decreased, but it reaches a minimum and then increases again. But what I have shown you is this that increases with temperature. So what is happening here? This is not what we are expecting. And this is not only occurs on gold. It occurs generally in metals as copper, silver, gold, and other metals with magnetic impurities. These are chromium, whatever. This occurs in lots of systems with magnetic impurities. So as a summary, we have different behaviors of resistance as a function of temperature. One is the typical one, that is a resistance that goes to a constant value. The second one is this one that we need to understand. And well, the third one is the superconductivity, that this is not the aim of this talk. Okay, what I have to say is that, okay, they found that it was about magnetic impurities, this effect, this resistance minimum, but there was not a theoretical approach, almost at least rigorous, until 30 years later. So this person, Jun Kondo, in 1964, he reported an article where he made a model in order to explain this resistance minimum. And well, he made perturbation expansion of a model. And when we say a model, when a quantum physicists say a model, it means a Hamiltonian. So I will present you a Hamiltonian. The system is basically metal with delocalized electrons and a magnetic impurity which has some spin, up or down. With this, we have the delocalized electrons, which this is described in second quantization. Second quantization, it means these operators destroy, these operators create an electron. Okay, we have the delocalized electrons, which are free particles in the metal, and the impurity. Well, at least not the impurity is the coupling, the antiferromagnetic coupling between of the impurity with the delocalized electrons. And we have several things. I'm going to explain each of them. First, here is the antiferromagnetic amplitude between the magnetic impurity and the delocalized electrons. This is the spin operator of the magnetic impurity. And this is the Pauli matrices, which kind of relates the spin operators, the spin operator of the impurity with the delocalized electrons. This couples both of them. Okay, this is the Hamiltonian. I'm not going to do some calculation, not anything, just to describe the system. The mechanism that generates Kondo, that generates the resistance minimum, is the following. We have the metal and the magnetic impurity, and we draw a diagram. In the diagram, we have the energy here. This is a Fermi C, which is the metal, and this is the impurity. Let's say that the impurity is filled with one electron, or, well, it has a spin down, for example. It can be up, doesn't matter. So what happens is that one electron with a spin up, in some moment, it fills the impurity, and suddenly it changes spin with impurity. This, then, right now, the impurity has spin up. So we have spin flip processes in the impurity. So all the time is doing spin flips in the metal. These spin flips, what they do, they make the resistance to become lower. To become higher. Sorry. So when this starts to contribute, a new term is need to with the model. A new term appears, which is this logarithm with the temperature. Okay, this term, he showed that it can fit experimental results. So it seems that that is more or less that it agrees with the experiments. There's what it was found, but there is a problem here, and I know you realize if we go temperature going to zero, the resistance diverges. So this model cannot be applied at very, very low temperatures. And the model, also with this model, we can define some characteristic energy scale to say when the model is valid or not. This is called the Kondo temperature. And it depends on the bandwidth. The bandwidth is the energy, basically the energy where it operates the system. rho is the density of the density of states of the metal, and J is the antiferromagnetic interaction. So this model, the Kondo model, it's valid only for temperatures higher than the Kondo temperature. Okay. This, of course, this model doesn't explain everything. So more techniques and models appeared along the years. Of course, we have the model I have introduced you. We have the equation of motion in the Anderson model that appeared late, more or less in the same time, but the explanation of the Kondo model appeared later. This is also valid for temperatures higher than the Kondo temperature. We have slave boson theories that it has the advantage that it defines at temperatures lower than T Kondo but not higher. And then we have renormalization group that is valid at any T, but it has the drawback that it only can be applied at equilibrium. So if we apply thermal bias or voltage bias, this cannot be applied. Okay, and this after these techniques appeared, people kind of stopped talking about the Kondo effect. But in the 90s there was a revival of the topic. And why was that? It was because nanostructures appeared. And then quantum dots were a really good system to study the Kondo effect. And first, let me explain what a quantum dot is. Quantum dot is a system where electrons are trapped in the 3 regions of space by quantum confinement. How they do it? Well, in semiconductor quantum dots, in the interface between two materials, they create a 2-dimensional electron gas, like a surface, an interface where electrons are free only in 2 dimensions. And then with some electrodes, we create walls. Like walls in the 2-dimensional electron gas, in such a way that in some region electrons can be trapped in all dimensions. With this, we can create a quantum dot. This can be studied also in other type of systems. Here, for example, we have a nanowire. In a nanowire, if we create a part where there is a different material than the material of the nanowire, we also create a quantum dot. So it can be created in different ways. What is good about quantum dots? They are easy to manipulate. These electrodes also can modify the density of states of the quantum dot. So we can modify the characteristics of the quantum dot really easy. One important thing is Coulomb interactions are not negligible, and this is very important for the Kondo effect, as we are going to explain in a moment. And then the quantum dot, if we don't make that the quantum confinement is total, we can study transport properties due to the quantum dot is coupled to fermionic reservoirs, which is the rest of the 2-dimensional electron gas. And then, well, this is more or less what a quantum dot schematically can look. We have the source and drain, which is the fermionic reservoirs, electrons, free electrons part, which are we have where it has a voltage, and then there is a gate where you can control the density of states of the quantum dot. And the importance of this is that quantum dots can be treated as artificial magnetic impurities, and this is an important thing about the Kondo effect. Okay, first let me explain about Coulomb blockade, which is important for explaining Coulomb blockade. Maybe you already know that, but since interactions are not negligible, well, first, in a system with two reservoirs, this is a Fermi C, this is another Fermi C, and the quantum dot has an energy level in the middle of these two Fermi Cs. So electrons can go through the quantum dot and a current is created. This is good. The problem is when the quantum dot is filled with one electron. Of course, we have two spins, so for the Pauli exclusion principle, it can happen. The problem is when the electron wants to go through the quantum dot, it has to reach an additional energy, which is the electron-electron interaction energy between the between the electrons inside the quantum dot, because they are so small that electron-electron interactions are really important. This is seen in experiments because when they measure the conductance as a function of the Fermi energy, for example, they see the peak of the level of the quantum dot and additional peaks due to this electron-electron interaction effect. And due to that, if you plot the conductance as a function of the gate, which controls the energy levels, and the voltage, applied voltage, what they find is that several diamonds, where inside the diamonds, the transport is forbidden. So this is called Coulomb diamonds, and it's a signature of the Coulomb blockade effect. In order to show you, I show you a picture where an experimental picture where we can see clearly see the Coulomb diamonds. Okay, let's talk about Kondo effect in this type of systems. A characteristic difference between the Kondo effect in metals is that right now instead of the resistance is the conductance, what depends on the logarithm of t. So this is kind of the opposite effect. So why is happening this? There's an actual reason. One is that in a bulk metal, in the case of the normal magnetic impurities, the electrons are delocalized and they can go freely and don't feel the impurity, or they can interact with impurity and go back. Of course, this is affecting in the transport in making it more difficult to travel. But for this type of systems, what is happening is that electrons has to travel through the quantum dot, the artificial impurity, in order to create transport. So right now, the Kondo effect what can do is to make more favorable to the transport along the impurity. Okay, this is the difference. I can show you that it actually happens. Here is conductance versus temperature in logarithmic scale, and as you can see, after some time it decays logarithmically. So it actually happens, this logarithmic dependence of the conductance. And additionally, I have to explain that this Kondo effect occurs at low temperature and strong Coulomb interactions. Why strong Coulomb interactions? I remember you that we need a quantum dot, only an electron in the quantum dot. We don't need two. And due to that, we need that the interaction energy has to be as large that any electron can go inside the quantum dot, inside the quantum dot when this is filled with only one electron. Okay. What you can measure, what you can find with these artificial impurities. So let's imagine quantum dot, and we have left and right lead, and you apply a voltage bias, and you can control the levels with a gate. So internally, what we find in the density of states is that you find at the Fermi energy a really narrow peak and peak. This is called Abrikosov-Zull resonance or Kondo resonance, and this is a signature of the Kondo effect. This Abrikosov-Zull resonance will create a zero bias anomaly in the conductance. At zero bias, V equals 0, a peak appears. This in the Coulomb blockade effect, this should be 0. So this is quite different from the other regime. And additionally, if we instead of tuning B, we tune the gate, what we find is that around some regime there is a plateau of maximum conductance. This is also related with a zero bias anomaly, because this occurs at zero bias. And additionally, when we combine these two, what we find is that in the Coulomb diamond, we find a line of conductance in the middle of the Coulomb diamond. And this only appears in once not in every, only in odd field when the quantum dot is filled with odd number of electrons. Why is that? Because of the spin effect. Because we need that only spin up or spin down. If there is the level totally occupied, the total spin is 0, and we cannot have this Coulomb resonance, this Kondo resonance. Sorry. Okay, let's put all of this in one box. I will come back later. I'm going to talk about thermoelectrics. I have to talk about a voltage. We know that induces electric current, and we all know that if we heat one extreme of a metal, a heat current will be generated, and we can measure, for example, the thermal conductance of this metal. But two different cross effects appears also in this kind of systems. If we find two dissimilar metals and we hit one of the streams, we will find electric current also. And this is called and we can measure with this electric current the thermoelectric conductance. So this is called this is part of the Seebeck effect. It's called Seebeck effect. Also, if we apply a voltage, it also can induce heat current. So with this, we can measure the electrothermal conductance. This is the Peltier effect. We are interested in this too in my work, in the work that I should explain at the end of the seminar. But right now that we know that we can apply a voltage or a thermal bias, I'm going to explain what happens in the Kondo resonance when we apply any of these non-equilibrium properties. One is what we know, the zero bias anomaly when we have the voltage bias, but let's look at the Abrikosov-Zull resonance. We can, with this, we studied two things: the position of the Kondo resonance and the width of the Kondo resonance. If we study this, what we find is that if we look at the position, we see that at some point it divides and splits in two resonances, and also we see how it is gradually destroyed the Kondo resonance as we increase the voltage. As example, here we have a Kondo resonance that it splits and it decays as voltage is increased. When we have, instead of a voltage, a thermal bias, what we find is that as it happens with the temperature, it decreases logarithmic well, not logarithmically, but it decreases with a thermal bias, and then reaches a regional scaling, and then the Kondo peak is completely destroyed. So a thermal bias also destroys the Kondo resonance. But right now, the work I have to explain is about two-impurity systems. So I have to explain about double quantum dots. Double quantum dots is an array of two quantum dots. The thing is that we can put the quantum dots in different configurations if we consider the two reservoirs. Can be parallel configuration, which both dots are connected with both reservoirs, or in serial configuration with these two are connected and only one of them sees one of the reservoirs. Additionally, we have new degrees of freedom because we can consider the channel coupling between the quantum dots, or the one electron in one quantum dot can feel the electron-electron interactions of the other quantum dot. So we have an interdot Coulomb interaction. In the conductance, what we find, if we see as a function of the both gates, is that right now we have hexagonal shapes, where it says when both quantum dots are occupied with n or m electrons, and every time we reach one hexagon is other region with different occupation of electrons in the double quantum dot. So right now we have more degrees of freedom, new configuration, so this thing is more complex. Okay, several effects that you can find in double quantum dots. One is the fan effect, which appears in parallel quantum dots, which is an asymmetric shape of the transmission function that it can be seen also in the conductance, as you can see here. Another thing is the orbital Kondo regime, orbital Kondo effect. Sorry, this is practically the Kondo effect, the normal Kondo effect, but instead of considering the spin, we consider the charge. We consider the electrons that if there is one electron here, one electron here. Another effect is called Pauli spin blockade, that due to singlet and triplet states between the two quantum dots can block the transport. But these are only a few examples. What we want to consider is the Kondo in these systems. And I show you an example here. They study two zero quantum dots, and they find different regions where they can find three different situations, which is the double quantum dot. Each of the dots is filled with only one electron, or a region where there is one totally filled, and the other one with one electron, and the third one which all of them are filled with electrons. In this case, we will find a zero conductance instead of a zero bias anomaly. In this case, we only have one impurity, so we will see a zero bias anomaly. And then, if we have only one in each of them will create a Kondo resonance, and they will interact with each other, creating two peaks, which will be a superposition of bonding and anti-bonding states. As you can know, if we have two levels and they have an interaction, a hopping interaction between these two, we can express this in expression of bonding and anti-bonding states. Okay, and one last thing about all of these systems is that is in this system, which is the system we are going to study. If we look at the internal coupling, we can define a superexchange interaction, which depends on the tunnel amplitude, the hopping between these two dots, and the interdot Coulomb interaction. With this, we can see that there is a crossover at some critical J. And what happens is the states where the crossover appears is when we have two Kondo impurities where these two Kondo impurities interact with each other, or we have a moment where we have a singlet state in between the quantum dots, and they are practically not interacting with the reservoirs. This will be important in the last part of the talk. With all of this, I can explain you the work I'm going to consider. The work I'm going to consider is exactly this one. I have already explained two reservoirs. The first one is going to be heated with some theta. The second one will be a constant temperature, but low, cold. And the two electrons will see each other by this tunneling coupling. We assume that they don't interact with electron-electron interaction between them. But the interdot Coulomb interaction, we imagine that is infinite. I described the model, so Hamiltonian, sorry. First, the lead Hamiltonian. This is more or less the same as in the beginning. This describes the electrons in these reservoirs. Then we have the quantum dots. Each quantum dot is described by a single level, and the tunneling coupling between each of them. And then we have the tunneling Hamiltonian. This describes the tunneling of the electrons between the impurity and the reservoir. One last thing, and very important, is in order to consider this correlate this model, we put a Lagrange Hamiltonian that what says is that the quantum dots has to be filled with only one electron. So the charge in each quantum dot has to be 1, and that's what we make with this Lagrange Hamiltonian. Additionally, we have this B, which is an operator which creates a vacuum state, and we are going to use this to describe this system. Additionally, this model is valid in the Fermi liquid regime. That means for temperatures lower than Kondo temperature. We assume mean field theory. The operator right now we are going to say that is a number. It will be a number which is its expected value, and we have to fulfill two conditions: the stationary limit and the Lagrange multiplier, which is assuming that the charge has to be 1. And the important thing is that we can study these two things: the Kondo resonance width that you already know, and the Kondo resonance position. Alpha will describe if it's left or right. Although this seems quite nice and good, it involves integrals and self-consistent calculation. So we have to apply a numerical calculation in order to explain the behavior of the system. Okay, what happened when we apply a temperature bias, a temperature difference, to the width of the quantum dot? This width of the quantum dots can be described as effective Kondo temperatures. We find 3 regimes described in these 3 of them. One is the weak, defining the weak coupling regime, because the tunneling between the quantum dots is lower than the tunneling to the reservoirs. In this case, what we find is each quantum dot kind of behaves independently from each other. The quantum dot which it's connected to the gold reservoir, it behaves practically constant. It remains practically constant, that will increase the difference. But the other one, it practically behaves like a normal Kondo system. So it decreases with temperature and then it reaches 0. Then we have the intermediate coupling regime where right now the quantum dot connected to the cold reservoir, it fills the other reservoir, but after some point, more or less around the Kondo temperature, it starts to behave independently, and the other one, as before, it decays to 0, destroying the Kondo peak. And the third one, we have a strong, really strong feeling of both behave more or less the same, but additional again at very large thermal biases, this is completely over. So one, it will behave as a normal system, as an independent system, Kondo system, and the other one is the Kondo peak is completely destroyed. So we are going to study here two things: the thermal current and the electric current, but due to these thermal biases. We study this, which depends on Fermi functions, which are the Fermi Cs, and transmission functions. Don't look at this. And we studied what is happening to the current as a function of the thermal bias. What we see is that it practically increases a lot, and at some point it reaches a maximum and it decays. Why it decays? This is not normal for the thermal current to the heat current. Sorry, this is happening because the Kondo resonance decouples from each other at large temperature bias. Additionally, we want to show that if we look at the thermal conductance as a function of the tunneling coupling, we see that it practically at low it obeys the Fourier's law. So and it has practically the same shape as we can find in the transmission. Okay, the second one is the electric current. What I like from the electric current is that the three regimes are practically clear. You can see in the thermocurrent the behavior of the three regimes. In the weak coupling regime, we see that it increases, it reaches a maximum, and decreases, and then it's zero always. In the intermediate coupling regime, okay, it increases, it reaches a maximum, but it slowly decreases to 0. So at maybe infinite thermal biases, it will be destroyed. And a strong coupling regime, what we find is that an inversion of the electric current. First, it will decrease, it will reach a minimum, then it will be decreased again, it will be positive, and then it decreases to 0. The behavior of this at the strong coupling is that instead of having one resonance, which is happening in these two regimes, what we find is a bonding, anti-bonding resonances. And these bonding, anti-bonding resonances are not located symmetrically. So this non-symmetrical shape of the transmission function, which is this part here, what makes is that at low temperatures, if the current flows through one resonance, giving the contributions to holes, and then it will get inverted at some point, and the electrons will start to dominate the transport. Finally, I want to talk about the crossover. The crossover I showed you before. In one paper, they showed that the critical component of the crossover depends on the effective condensed temperatures in this way. And so what we have done is that we have say, okay, let's look what happens to this constant when we apply a thermal bias. And what we see is that basically it changes from this point, from 8 pi, kVt gamma R, or the Kondo temperature of the cold reservoir, and it decreases, and then it reaches another constant value. So the crossover still appears, but it happens in a different moment. Additionally, if we look as a function of the tunneling, what we see is that correlations are reinforced. Okay, with this, what I want to say is that I hope that you have understand the importance of the Kondo effect, and that there is still lots of things to study about the Kondo effect, because we have lots of systems, there is not the perfect model, and there is a long way to cover, to walk about this phenomena. And then about the work we have explained, the take-home message is that we have found three different regimes where we can see it directly in the transport, at least in the electron transport. With this, when this take-home message, I want to thank you all for your attention.
Historical question. The Kondo effect was one of the highlights of the renormalization group by Wilson. He developed the renormalization group.
Yeah.
He applied that to the Kondo model. He was one of the highlights
at
the time. And what happened to your problem? Is there still flow equations to analyze, or what happens to the application of the renormalization group to the Kondo problem in quantum dots?
In quantum dots, you can still do it. People are doing it already.
You don't need to do it.
Eh?
You don't need.
Well, you can do it if you want. What I have shown you is at temperature lower than the Kondo temperature. The problem of the renormalization group is that when you have two different temperatures, it's difficult to apply it. Or just few people have applied, but it's very blurred what they have done. It's difficult to implement because it happens at equilibrium. The Wilson renormalization group can be applied at equilibrium at equals 0, basically. So that's why. Yeah, no, it's true, and there are few works, but it's not. Still, this requires a strong computational power that maybe you don't have, and it's good to have easier models to understand what is happening in the Kondo effect.
There's a basic question of basic solid states, because I don't know enough of that.
Mm-hmm.
What is in the original Kondo model? It happens when you have a metal, you put a magnetic impurity on it.
Yeah.
What is this? I mean, a metal, I understand, is something having 3 electrons. The magnetic impurity, what is this? Is an atom or something having
it's an
only
atom.
1 electron in the last shell? So instead of magnetic impurity, you put a sulfur, or you put a non-metal. What is the difference?
What is happening? As I have said, the process is different in the transport. But in a normal metal, what we have is a magnetic impurity. This is that the last shell is only filled with 1 electron. So it can be up or down the electron spin of the electron in the last shell. So this can interact with the localized electron, the conduction electrons, in such a way that the electron spin is changing all the time inside the impurity.
And then the quantum dot, the analogy with the magnetic impurities, because by construction you can have only 2 electrons in the...
Only one.
Or
two, but if you... Exactly.
This is the equivalent with the real impurity, with the atomic impurity.
Exactly. So a quantum dot has to have be constructed in such a way that the electron-electron interaction is quite high.
You can only have one, the other
Exactly.
blocks.
And this is more or less artificially we have what it happens in the metal.
Okay, so just a clarification for the electromagnetic impurities. I mean, Miguel mentioned this SD model. So S is for the electronic waves in the metal, and D is for the impurity, which is typically iron, manganese, which they have this D shell, which is half filled. Okay, so that's but you can have like magnetic impurities, for instance, where the shell is the F shell, which is actually, and then you have all these heavy fermions materials. So I think it's let's say quite universal. So my question to you is, when you show this critical differential coupling as a function of charge temperature, can you show me this line again? One of the last ones.
One of the last ones, yeah. This one, right? Right?
No. When you show your results.
My results, yeah.
The last one. If you go later. So we have this antiferromagnetic coupling to the two.
This.
Yes, this is. Okay, so you are considering temperature difference 100 bigger than the Kondo temperature.
Yeah.
This goes beyond the validity.
Yeah, it goes beyond the validity, but at least around the Kondo temperature, we can expect more or less the same behavior. But what we know is that the validity is for the background temperature. That's we have to take into mind. That the background temperature is still small.
But still, this is very far from equilibrium.
Yeah, this is very, very far from equilibrium. Yeah.
Have you considered how easy or difficult is it to measure these different scenarios in the double dose experimentally? I mean, what are the temperatures you expect?
I haven't made any calculus, but I have to.
For experimentally, to have an idea of what is the scale at which the experiment should be designed.
I have not made calculus so far, but I have to say that this is quite difficult to apply experimentally. First of all, because apply thermal gradients in the small scale is very difficult. It requires a really strong, devices, really strong machines that can do this, and then it's measuring. Measuring can be even worse. If for the electric current, it's okay, but if we
I think there are experiments doing thermoelectric.
Yeah, no, there are experiments. But there is only one, and we think that they have stopped doing experiments because the large effort it requires. Yeah.
So there's nothing of specific device or application in this.
Well, we have thought that it can this dramatic change of the thermal heat current, it can be applied in some way because it increases a lot with temperature. So we can find some kind of device which can take profit of this, but nothing else.
Actually, it's very interesting because you can see the heat current here decreases at some point.
Yeah.
When the heat increases. So there is a, let's say, negative differential thermal resistance. And there are not so many systems showing that.
Yeah. if you are in the particle Hall symmetry point, it means that for only our Kondo resonance, which is in the middle of the both levels, level and the Coulomb blockade level, this can be interesting to find.
Maybe for refrigerator, solid state refrigerator.
Yeah, maybe.
There's no other question. Let's thank Miguel again.
Vale.